we talk about stratospheric chemistry, and today we will move to the troposphere and down to the surface to discuss again about chemistry, and we will see some differences with the stratospheric chemistry, but we will see as well some of the chemical compounds we introduced yesterday. We will see that they play a role as well in the tropospheric chemistry. First, let's start with a general introduction on tropospheric chemistry. So, if you remember, during the first lecture, during the first lectures, we mentioned that the atmosphere is an oxidizing medium. We introduced the idea of oxidation state or oxidation number. And in the atmosphere, the oxidation reaction is very important because it can remove some pollutants as, for example, methane or carbon monoxide or halocarbons that we saw yesterday. They are involved in the catalytic loss cycles related to chlorine oxide radicals. So what happens if we want to summarize the whole process? We have some emission from the surface up to the atmosphere of some reduced gas that can then be oxidized by some processes, by some compounds, and transform in oxidized gas, and they can even move from the gaseous phase to the aerosol phase, and then they can be uptake through different processes, dry deposition, wet deposition, and it will re-enter the cycle and will be reduced in the soil. So this is the general mechanism. However, the idea that the troposphere, that this oxidation reaction could take place in the troposphere is quite recent, because in the 50s we thought that the troposphere was chemically inert. We thought that species to be reduced, they need to travel up to the stratosphere where they can be exposed to hydroxyl radicals, to the hydrogen oxide family, and they can be oxidized and consumed. The knowledge about stratospheric chemistry for the hydroxyl radical, OH, started developing in the 60s, but still at that time little was known about the photochemistry in the troposphere. And actually we thought the methane and carbon monoxide were chemically inert in the troposphere. And so, for example, the first estimate of the lifetime of carbon monoxide was around 3 years. So there was a lot of concern about the increasing in traffic, in urban traffic, because carbon monoxide is one of the main products of combustion, and so the increase in urban traffic and in the use of cars and the car emissions lead to a big concern about the global pollution due to this large source of carbon monoxide that would have stayed in the atmosphere for a long time. So this was the first idea about the troposphere as a chemically inert part of the atmosphere. Then some breakthrough happened. The first one is that scientists discovered that actually the lifetime of carbon monoxide was shorter than 3 years, was around a few months. And so this required a tropospheric loss, since we have a large amount of carbon monoxide that are emitted, and they didn't stay in the atmosphere for such a long time, so something should happen to this gas. The second breakthrough was the discovery that OH, hydroxyl radical, is present in the troposphere. It can be produced. And this lead to, as well, the third breakthrough was to try to try to assess the amount of hydroxyl radical in the atmosphere. This was a bit challenging because this radical has a short lifetime. So now we can measure, we have instruments that can measure the amount of hydroxyl radical with still some uncertainties, but the instrument have improved with time. But back in the 70s, this was still very difficult, and so an indirect assessment has been done based on the emission of methyl chloroform. This gas is mainly produced by industrial activities. It's part of the halocarbon family. And so we have the industrial inventories that estimate the production of this gas, the amount that is then be released in the atmosphere. And so, and the main sink of this methyl chloroform is a reaction with hydroxyl radical. So indirectly, by knowing the amount, we will see just in a moment, by knowing the amount of this methyl chloroform and its lifetime, the reaction with hydroxyl radical, we could then estimate the amount of hydroxyl radical and its lifetime. And then the history continued, because then the study of the tropospheric photochemistry goes on, in particular applied to smoke mechanism, to urban environment. Then the mechanism related to the oxidation of methane had been better understood, with finding that this mechanism releases carbon monoxide and formaldehyde, and then as well mechanism related to the reaction between hydrogen oxide radical and organic radicals with nitrogen monoxide. And so what we can see is that in general, then the understanding of the tropospheric photochemistry goes on in understanding as well the role of some important actors that we will see later, that are the radicals belonging to the hydrogen oxide family, HOX, and the nitrogen oxide family, NOx. And as well, we will see the role of methane and carbon monoxide in the whole story. But the first actor that we need to introduce is the hydroxyl radical in the troposphere. So we have seen hydroxyl radical yesterday. If you remember, it is produced, firstly you need the photo dissociation of a molecule of oxygen, and then that release a single atom of oxygen, and then you need water vapor that will react with the single atom of oxygen to produce two hydroxyl radicals. However, now we are lower in the atmosphere, so we have to take into account the fact that there will be less photons that will reach the troposphere. And we can see here, so here we have the actinic flux has a function of wavelength and is represented at different altitude in the atmosphere, at 50 kilometers, 40 kilometers, till down to the surface, 20 and 0 kilometers. So the actinic flux is the number of photons that hit an horizontal unit surface area per unit of time, and here it has been normalized by the wavelength. And here the green band represents the window, the range of wavelength in which hydroxyl radical can be produced in the troposphere. So you need this range of radiation of photons, and you can have this range of photons that can reach the surface. And these photons, what they can do is that they can photodissociate ozone. So the primary source of hydroxyl radical in the troposphere is the photodissociation of ozone that release a single atom of oxygen that can can react with water vapor to produce 2 hydroxyl radicals. So this mainly we have seen yesterday for the stratosphere, but what is important to remember that here in the troposphere we only have ozone that can lead to a production of single atom, and if you want to, and here this 2 graphic shows you why we ended up with this narrow band of wavelength in which we can produce, in which ozone can be photodissociated, is because if you remember about photolysis and how we compute a photolysis rate constant, we need to multiply 3 factors. One is the actinic flux, so this the solar flux in the range we are interested in. Then we have the ozone absorption cross-section, this bold solid line, which is the section in which ozone can absorb an incoming photon in this range of wavelength. And then we have to multiply this cross-section with the quantum yield, that is the probability that the photon will lead to photodissociation. And so finally we ended up with this range of wavelength under which all the conditions under which we have a high probability that the photodissociation can happen and that the ozone can absorb the incoming solar radiation. So the primary source of hydroxyl radical is mainly in the troposphere is photodissociation of ozone. And the main sink is the oxidation of carbon monoxide and methane. So hydroxyl radical can consume carbon monoxide and methane, and we now know that the amount of hydroxyl radical is around 10 at the 6 molecules per cube centimeters, and it has a lifetime very short of around 1 second. And to estimate these numbers at the beginning was very challenging because, as I told you, due to its short lifetime, the first instruments were very uncertain. So what has been done, scientists find an indirect way to estimate the amount of hydroxyl radical, and so they use this methyl chloroform that is uniquely produced by human activities. It's an industrial solvent that has been then banned by the Montreal Protocol in 1989, and his main sink is the reaction, the oxidation of this methyl chloroform by hydroxyl radical. And so what we know here, this graph only shows the evolution of the mixing ratio in methyl chloroform from the 90s till 2010. Before the 90s, what we had been observed, it was an increase in this methyl chloroform, in this production and use. And then with the Montreal Protocol, the production of this gas has been banned, and so then we observe a decrease in the amount and the mixing ratio and the concentration of this gas in the atmosphere. So how do they use the numbers about methyl chloroform, the industry statistics, to then draw information on hydroxyl radical? Well, if we know that, so this M represents the mass, the concentration of this methyl chloroform in the troposphere. Here we are looking at the change in concentration with time for this gas, and we represent this as related to mainly 2 processes. One is the loss rate due to the reaction with hydroxyl radical. So here we see what we have seen already many times. So the reaction rate, so is a loss, so there's a minus, there's a rate coefficient that can be measured with laboratory experiments, and then we have the amount of the 2 reactants, hydroxyl radical and methyl chloroform. Then we account for the exchange with the stratosphere. However, these are quite small, so we can reduce we can reduce our equation just to this part. And so from here, then we can define the number density of hydroxyl radical in the troposphere as a ratio between these two terms, where all the terms can be or measured with laboratory experiment, as for example the rate coefficient, or derived from industrial inventory, industrial statistics about the amount of this gas that has been produced and then released in the atmosphere. And so the first estimate that is quite close to what has been then measured is that the number density of hydroxyl radical is this 10 at the 6 molecules per cube centimeters that then influence the lifetime of carbon monoxide, that is around 2 months, and the lifetime of methane, that is around 9-10 years. And so we have seen that to have hydroxyl radical in the troposphere, we need ozone. And in fact, we have seen yesterday when we start introducing ozone, we look at firstly at the vertical profile for ozone, as we are looking here. So vertical profile of the, here it's given as an ozone partial pressure. So the black line represents measure from sounding, while the blue line represents mean over March over a decade over the 90s. And so you see, as we mentioned yesterday, that 90% of ozone is founded, you can find it in the stratosphere, while, however, we still have 10% of ozone that is in the troposphere. So for those that just arrived, we are starting discussing tropospheric ozone. Then I'm sorry, I just realized today that I was not recording the previous lecture. They told me to hit the record button. So now I'm recording, so hopefully today and Friday they will be recorded. I'm sorry for the previous lecture. So about the tropospheric chemistry, just a short summary of what we have seen together with your colleagues is that at the beginning it was thought that the troposphere was chemically inert. Then we understood that it was not, because we can have some radicals that can be formed in the troposphere, and one of these radicals is the hydroxyl radical that we have seen, that we have introduced yesterday with the stratospheric chemistry. This tropospheric hydroxyl radical is mainly produced by the photodissociation of ozone. And now we are just introducing tropospheric ozone, and then we will continue the story about hydroxyl radical and what it is, its role. So tropospheric ozone is 10% of the total column of ozone. Where it is found? Well, mainly it is found over industrialized region. For example, here we are looking at the spatial distribution of tropospheric ozone as observed by satellite observation for 2006. We have the seasonal means for spring, summer, autumn, and winter. And as you see, high level of all tropospheric ozone are located during spring and summer over the mid-latitude. And as well, they are also located over a region where biomass burning takes place. While minimal values are located over the ocean, because we have less sources for tropospheric ozone, and so the destruction, so the chemical loss is dominant. And what we have observed is a rise in tropospheric ozone over the 20th century. So here, these are measurement observation at mountain sites in Europe, so places that are quite remote from, we can't measure ozone like in a city center or close to a city center, so we choose mountainside as a place where we can measure a kind of pristine atmosphere. And so what has been observed is the mixing ratio of ozone has increased, what has been measured at this site has increased in the last century, and the pre-industrial value was around this 20-30 ppb. And why do we care about ozone, tropospheric ozone is, if you remember yesterday, is that in the upper troposphere, ozone is a greenhouse gas. However, he has as well an important role for maintaining these hydroxyl radicals that we just mentioned before. He has a role because it's a main sink for carbon monoxide and methane. There are two important pollutants. So in the lower middle troposphere, ozone also plays a good role because it maintains the amount of hydroxyl radicals. So then we started the lecture by saying that at the beginning, scientists, we thought that the troposphere was chemically inert, that nothing was happening there. That actually, we thought that carbon monoxide and methane were chemically inert. So also at the beginning, scientists tried to apply the same mechanism that they have studied in the stratosphere to the troposphere. However, this couldn't work because, for example, what we have seen yesterday is that in the stratosphere, we mainly have the Chapman mechanism plus a catalytic loss cycle. So mainly we have the photodissociation of oxygen that release single atom of oxygen that can then produce ozone. Then ozone can be photodissociated, and then we have as well the action of these catalytic loss cycles that can consume ozone. However, in the troposphere, if we look at the same graph that we looked yesterday, we know that at the surface, the flux, solar flux, the radiation that can reach the surface, so we just look at this solid line for surface. This is the number of photons that can reach the surface, and if you see, they spread over this range of wavelength. And so, take into account the absorption cross-section of both ozone and oxygen, we understand that in the surface and in the troposphere, we can't have the photodissociation of oxygen at work because we don't have photons with enough energy to split a molecule of oxygen. So in the troposphere, we don't have photons with a wavelength lower than this threshold, so the oxygen photolysis can't take place. And so we have a small amount of single atom of oxygen that are produced and that can trigger these catalytic loss cycles that we have seen yesterday related to the hydrogen oxide family, the nitrogen oxide family, and the chlorine oxide family. So another idea was, so maybe the ozone in the troposphere maybe comes from the stratosphere. But this as well can't work because if we try to estimate, to do a back of the envelope calculation, so a rough estimation of the ozone flux across the tropopause from the stratosphere to the troposphere, this is around 10 times 10 at the 13 moles per year. And now we know that, so the photodissociation of ozone will produce two hydroxyl radicals. We have seen this in some previous slides. And this hydroxyl radical is the main sink for methane and carbon monoxide. If we now account for the source of methane and carbon monoxide, we ended up with these numbers. And if we add together the source of methane plus the source of carbon monoxide, we ended up with a number that is much larger than the 2 hydroxyl radicals that can be produced from this amount of ozone coming from the stratosphere. So finally, what will happen is that due to the large abundance of carbon monoxide and methane, all the hydroxyl radicals produced only by the ozone coming from the stratosphere will be completely consumed. So the second hypothesis can really work. So the first was, okay, maybe we can just apply the same reaction we have seen for the stratosphere in the troposphere, but we don't have one ingredient, we don't have the photons with enough energy for the photodissociation of oxygen. The second idea is, okay, maybe the ozone comes from the stratosphere, but this, if we do a simple budget, it doesn't work. And so we have to, and so at that point, some breakthrough occur when the scientists better understood the oxidation of carbon monoxide and methane and their role in producing ozone in the troposphere. So first, let's introduce carbon monoxide and methane. So carbon monoxide is mainly produced through incomplete combustion. So here we are looking at sources and sinks of carbon monoxide. As you see, the main sources are related to fossil fuel combustion and biomass burning. Also another important source is the oxidation of methane. And the main sinks instead is the oxidation by hydroxyl radical, and we ended up with a lifetime for carbon monoxide of around 2 months. Here we look at the distribution of this carbon monoxide over the globe. So we see that large sources are found, for example, over biomass burning region, or as well a region where domestic burning, domestic heating and domestic burning is used, over China, for example. If we now look at methane, so the main sources is wetlands, and then other important sources are rice croplands, animal husbandry, and as well some energy sources as gas and coal. And we have discussed about methane related to the carbon cycle. The interest for methane emission is growing because this is not just an air pollutant, but as well is an important greenhouse gas. And it has a lifetime of around 9 years because the main sink of methane is the oxidation by hydroxyl radical. So now we really dive into the chemistry of the troposphere. We'll see we have 2 slides full of reactions. I don't want you to remember all the reactions because even for me it's a lot. But I want you to really grab the main meaning of what is happening there and why carbon monoxide and methane are related to tropospheric ozone, and as well we will meet the hydrogen oxide radicals, HOX, that we saw yesterday, and the nitrogen oxide radicals. But yesterday we saw that they were involved in the destruction of ozone, while in the troposphere they are involved in the production of ozone. So really having to have in mind this difference between the stratospheric mechanism and the tropospheric mechanism. So let's start with the oxidation of carbon monoxide because it's shorter. So when we have one molecule of carbon monoxide that is emitted, it can be oxidized by hydroxyl radical, OH, and produce carbon dioxide and another radical, hydrogen, still of the family of hydrogen oxide radicals. Then this can go through this other reaction to produce hydroperoxyl radical, HO2. And this hydrogen peroxyl radical can then react with another radical, the nitrogen monoxide, to produce nitrogen dioxide that can then be photodissociated in the presence of oxygen to produce ozone. So we can already just stop here to analyze this system of reaction, and the net of this system of reaction is that we have one molecule of carbon monoxide that is oxidized in the atmosphere to produce one molecule of ozone. Okay, so here we see how the presence of hydroxyl radical and of other member of its family, the hydrogen oxide family, plus the presence of nitrogen oxide family finally lead to production of tropospheric ozone. Then there are also some other reactions that can take place in parallel, and they are related mainly to this to these reactions, because here to this reaction, the hydroperoxyl radical HO2 can react with nitrogen monoxide, or it can go through as well self-reaction, so react with another hydrogen hydroperoxide to produce these. I always forget the name. The hydrogen peroxide. Maybe do you prefer that I write the name, or is do you? Yep. Okay. So we have seen. Maybe I put O here. So this hydrogen peroxide, H2O2, can be or photodissociated, so hit by a photon and produce two hydroxyl radical, OH. So in this case, you see that actually the production of this hydrogen peroxide of this compound can actually trigger even more the free of more radicals, because if it goes through this reaction, then we have even two more hydroxyl radicals that are produced. So in total, we could have three hydroxyl radicals that are produced, one here and two here. So this, by producing this hydroperoxyl radical and then this hydrogen peroxide radicals, we can then having up to three hydroxyl radicals that are produced. In the other case, it can otherwise be oxidized by an hydroxyl radical. So in this case, it consumes one of the hydroxyl radicals, and this leads to the production of water vapor and hydroperoxide. Yeah, so it's important to think that through like this way, you can have even an acceleration in the chain reaction, or you can otherwise consume part of your hydroxyl radical. But this, what we are looking at, are these radical-assisted chain reaction, where you can always have some branching reaction that can accelerate your system of reaction, or not if another reaction can take place. So now we move to the oxidation of methane, which is involves more reactions. What we want to, what we focus on is that firstly, we have the oxidation of methane by hydroxyl radical. This produces water vapor. So we mentioned this, I think, when we introduced methane, to take into account that this process also increased the presence of water vapor in the atmosphere. And then we have a number of reactions that involves always these radicals belonging to the hydrogen oxide family, as hydroxyl radical or hydroperoxyl radical, and as well they involve the nitrogen oxide family. What is important is that through this reaction you can produce formaldehyde, this CH2O, that can be oxidized by hydroxyl radical, or it can be photodissociated, and for example in presence of oxygen, this can lead to the production of hydroperoxyl radical, and this can then lead to the same fate of reaction that we have seen for the carbon monoxide, and then lead to the production of ozone. However, for methane, it's not so simple as for carbon monoxide, the relation with the nitrogen oxide family. In fact, we have to distinguish two cases. So, methane oxidation depends on the amount of nitrogen oxide radicals. So, if we have nitrogen oxide radicals, what happens is that finally, if we want to, let's try to jump to the conclusion, so then maybe we can go back. So in the presence of high levels of, or in the presence of nitrogen oxide, what happens is that methane is oxidized, and this leads to the production of 5 molecules of ozone and 2 hydroxyl radicals. So ozone is produced, and as well hydroxyl radical to maintain the reaction system. Instead, if there are no nitrogen oxide, the oxidation of methane consume hydroxyl radical. These 3 hydroxyl radicals are consumed, and it doesn't produce ozone. So really the fate of the oxidation of methane not only depends on hydroxyl of the hydrogen oxide family, but it depends strongly on the nitrogen oxide family, on NO. And so, and this 5 molecule of ozone is because from the here. So if you look at the we always look at this branch, the production of this hydroperoxyl radical, because this is produced and it reacts with nitrogen monoxide, then it can produce nitrogen dioxide, and then this, through the photodissociation, can produce ozone. So if we want to count this 4, here you have, so 1, 2, 3, 4 of this hydroperoxyl radical are produced through this reaction I'm pointing at. And so we have 4 nitrogen dioxide that are produced, plus you have nitrogen dioxide that is produced here through the reaction between nitrogen monoxide and CH3O2 is methyl peroxy radical. So we have 4 of this nitrogen dioxide that are produced here, plus 1 that is produced by here the oxidation by nitrogen oxide of this methyl peroxy radical that produce one other NO2, and so finally you can produce 5 molecules of ozone. So the main what is important here to if we try to make a link between everything. So in the troposphere, we need ozone to produce hydroxyl radical through the photodissociation of ozone. The hydroxyl radical OH is an important product because it can consume some pollutant as methane and carbon monoxide, but it can't act alone. It also needs nitrogen oxide for the oxidation of this carbon monoxide and methane. And this process naturally will produce some ozone. It's just that now today we have more and more sources of carbon monoxide and methane that are being emitted, and so this accelerates the production of tropospheric ozone that in part has like a good role because it maintains the amount of hydroxyl radical that is often called the cleaner of the atmosphere because it can consume some pollutant. But on the other side, ozone in the troposphere acts as a greenhouse gas. So you have to balance all of this information. And we have introduced nitrogen oxide as an important actor in the reaction that we look at. So we have seen how nitrogen oxide is formed up in the atmosphere by, for example, lightning or combustion in aircraft. But it's mainly, in general, it's produced through fuel combustion, fire, and as well microbial activity in the soil can also release nitrogen oxide. Here we see a picture that we saw at the very beginning showing the tropospheric column of nitrogen dioxide and the spatial distribution of these NO2 columns. That depending on the satellite you use, here is focusing on the troposphere part of the atmosphere. So here we look at the pie chart of Nox emission, and you see that the main emission comes from fossil fuels, followed by biomass burning, and still lightning as plays an important role, especially in the tropics. And one member of the family of nitrogen oxide is as well PAN. So in general, what happens is that when we have emission of nitrogen oxide at the surface, already the exchange between NO and NO2 is very fast. It takes 1 day. So usually they don't travel so far. To travel far from the region where they have been emitted, they have to be transformed into another form as peroxide acetyl nitrate, that is also called PAN. So this is produced through the reaction of nitrogen oxide with carbonyl compounds. So these are a product of the oxidation of hydrocarbons. So just remember that this NOx can then be transformed in a new compound, this PAN, and this PAN is thermally unstable. So depending on the temperature at which it is exposed, its lifetime change. So if it can travel up in the upper troposphere, then it is exposed at lower temperature, so it's more stable, so it can travel far away from the region where the nitrogen oxide has been emitted. And so at that point, then it can it can go through subsidence and be thermal decomposed, because then this compound is exposed to higher temperature while it's going down in the atmosphere. Then nitrogen oxide can be released, and then we find the process that we have already discussed, the conversion of nitrogen oxide into nitric acid that can then be scavenged mainly by rain, so wet deposition finally close this cycle. And this and we can, for example, have a look to this aircraft measurement that has been done over California, and that witnessed air pollution plumes coming from Asia to the United States. So this campaign has been done in 2002 between April and May. So let's try to discuss together what is observed here. So on May 5th, what do you see? You see a plume that is where we have high levels of carbon monoxide, the black line, and this PAN, which is in the family of this nitrogen oxide. And then we have some like, yeah, we have ozone. Ozone is already quite high, but we are over some polluted region, so production of ozone can already be there. While we have lower value, for example, of nitric acid and NOx that has been measured at this 6 kilometers of altitude. Okay. Then a few days later, the aircraft also cross the same plume, but at different altitude in the lower part at 2 kilometers. And what do you see?
Some increases in some of the species.
Yeah, exactly. We see that partly the carbon monoxide has been consumed, so has been oxidized, and we have seen before that when carbon monoxide is oxidized, it produces ozone. And in fact, we see that now we observe some peaks in the ozone profile. And what we see for PAN, so we have said that PAN is kind of a form of nitrogen oxide that can be transported far away, because when it goes up in the atmosphere, it is exposed to lower temperature, it's more stable, but when the plume is subsidizing, then it is exposed to higher temperature, and so finally it releases nitrogen oxide, and this nitrogen oxide then is converted into nitric acid. And so here we can really, with this few information of the chemistry in the troposphere, we can understand what's going on in this plume. And then through, for example, if you apply a path model, the model that follow like a volume of your air, they can then reattribute the origin of this plume of polluted air. So then attributing, so the one reason we can attribute this plume to somewhere pollution is that you have PAN, and as well the plume is already like sitting at a high altitude, is not related to, for example, what has been measured by air quality stations. And then as well you can apply a model to like do the backward travel of your plume to find where it could have been emitted, related as well to the weather condition, the meteorology of the region. And so here we try to put everything together. So we have the nitrogen oxide family with NO and NO2. The cycling between these two is very fast, is around 1 day. They are nitrogen dioxide. We have seen that is involved in the production of ozone through the photodissociation. And then we have seen that this, for this family, we have introduced already yesterday some reservoir species. One is the PAN, that is that can be, it's only kind of a temporary reservoir, because then it can, related to the temperature, can then release back some nitrogen oxide, while some other reservoirs are the nitrate, the nitric acid, and the dinitrogen pentoxide, NO2O5. And we have seen that the main form of this, how this nitrogen oxide can be scavenged, is when it is transformed into nitric acid, then this is highly soluble into water, so then it can be scavenged by rain. And one other thing is that you have also to always remember that some reactions can take place during the day. For example, when we have sun, we can have photodissociation and the presence of hydroxyl radicals, while some reactions, however, this can happen during the night, and so you have always kind of during the day you have production of some compounds, while during the day this production can't occur anymore, and so you have other compounds that are accumulated there as a form of reservoir. And so this, in this way we see nitrogen oxide and hydrogen oxide are related to the tropospheric ozone. So here is a scheme to summarize all the processes that we have seen so far. Well, methane is missing, but we have carbon monoxide. And so here it's more a way to remember that through the oxidation of carbon to produce ozone, you also need nitrogen oxide, and then that this we will comment later. That so the production of ozone really depends on the nitrogen oxide amount that you have in your mass of air. And we see this more in details for the ground surface. So at the ground, ozone has a bad role because it's toxic for humans and vegetation. And as well, we will see a different kind of recipe to produce ozone. So in the stratosphere, we have seen that mainly ozone is produced. The first process that leads to production of ozone is the photodissociation of oxygen due to ultraviolet radiation. This can occur in the troposphere, where we have seen that carbon monoxide and methane play an important role, together with the hydrogen oxide and the nitrogen oxide family. At the surface, the main recipe is related to the presence of carbon monoxide, volatile organic compounds that could also include methane, and nitrogen oxide plus sunlight. So in general, you have production of ozone when you have a sunny day, warm temperature, and also some weather conditions can favor the smog related to ozone. For example, over Los Angeles, you may have seen already one of these pictures. So the brown cloud that you see here is mainly associated with nitrogen oxides. Nitrogen oxide plus volatile organic compound plus ultraviolet radiation, so plus the sun, is already a good recipe to have production of ozone. Moreover, if you have, for example, a temperature inversion, then you have kind of the air that is really trapped in the boundary layer. The vertical mixing is not so efficient, and this so also like the ozone chemistry is the ozone pollution, sorry, not just depends on the chemical compounds that you have in an area, but as well it depends on the weather conditions that you have, because you need light and warm temperature. And here, and looking at the ground surface ozone, we introduce a new chemical compound that plays an important role in the production of ozone close to the surface. They are called the non-methane volatile organic compounds. So they can partly of that are produced from industrial activities as a solvent or some like to paint. Paint. Yeah, and but then just looking, so partly is also produced by biomass burning. But if you look at the numbers, you see that the amount that is emitted by the vegetation is much larger than what can be associated, for example, to anthropogenic activities. So in fact, plants emit a large amount of this non-methane volatile organic compounds, so that if they are called this way, methane is not included. Otherwise, it can be also included when it's called methane volatile organic compounds. And so they are emitted by plants for many reasons, like plants emit these volatile organic compounds it seems to protect the plants for thermal stress. As well, actually, these volatile organic compounds are the essential oils. I don't know if you have ever smelled an essential oils, or if you have, for example, walked into a forest of pines on a sunny day, or here on the castle. Or even here, I think there are some pines. The fragrance that you can smell, that are volatile organic compounds. And the plant emits that as well to, for example, to attract some pollinators, so to kind of ensure its
Existence.
yeah, as well how to say to repel all the insect that could be that could attack the plant. So the plants can emit these compounds as well to send a signal to other plants. There are many studies from biologists that are really trying to understand why the plants emit these volatile organic compounds. Not all the plants can emit a large amount of this VOC. For example, wood plants, trees mainly emit this VOC, while grassland or croplands emit less of these volatile organic compounds. And these compounds can be actually seen from space. Here, for example, you have a satellite measure of formaldehyde, that is a product of the oxidation of these volatile organic compounds. And this picture has been taken, this measurement has been taken over the contiguous US. And you see there's a large production, there's a large amount of formaldehyde. So again, byproduct of the oxidation of these volatile organic compounds. There's a large source of this formaldehyde over the eastern US, and here you have a large extension of forest of pines, as well of I forgot the name, not conifers, the deciduous trees, the tree that have the leaves that fall during the winter time. And so these kind of trees, the conifer or deciduous, are large emitter of volatile organic compounds. And if we now look at, for example, some percentage of the total nonmetal volatile organic compounds over the globe and over different continents, so we see that over the globe, the non-anthropogenic part, mainly isoprene. Isoprene is one form of, is one compound in the large family of volatile organic compounds. So as you see, non-anthropogenic volatile organic compounds cover 80% of the total of volatile organic compounds. Then the percentage change depending on where you are, like in Europe is the sharing is 50-50 between non-anthropogenic and anthropogenic volatile organic compounds, while, for example, North America there's a large emission of volatile organic compounds, and there is an increasing interest towards these volatile organic compounds because they are involved in the chemistry of ozone, as we are looking here, but as well they can, we will see this tomorrow, they can lead to production of aerosols, the so-called secondary organic aerosols, and they are also involved since they consume hydroxyl radical for their, they are oxidized by hydroxyl radical, they can remove part of the sink for methane, and so they can they are kind of competing for the hydroxyl radical with methane, and if we reduce one of the sink of methane, you imagine that methane will sit much longer in the atmosphere. And as well, another reason we are interested in these volatile organic compounds is that compared to like carbon monoxide and methane, where we know that most of the sources are related to human activities, for volatile organic compounds, everything depends on plants, and we don't know how plants could change the amount of the emission of these volatile organic compounds with under a changing climate. So the deal is really to understand how how the emission of volatile organic compounds could evolve under a different climate, and this involve not just chemists or physicists, but as well biologists, ecologists, really to understand how the vegetation will work under a different climate. So, but let's go back. So we introduce, so today we are talking about tropospheric chemistry. We have already seen that tropospheric ozone can be produced through the oxidation of carbon monoxide and methane in the troposphere. Then now we are getting close to the surface. We can have large amount of these volatile organic compounds emitted by plants, for example, and so they can play an important role in the ground surface ozone. Why we introduce also these members together more than methane and carbon monoxide? Well, volatile organic compounds are more reactive than methane and carbon monoxide. They have a shorter lifetime than methane and carbon monoxide. They have a lifetime of few hours, few days. So they react faster than methane that has a lifetime of around 10 years, or carbon monoxide that has a lifetime of around a few months. So if methane and carbon monoxide can travel like up in the atmosphere, volatile organic compounds are mainly oxidized as soon as they are emitted. So here we represent this generic hydrocarbon, this generic volatile organic compound, as RH is oxidized by hydroxyl radicals. And then here we have as well, again, the production of new radicals, R, that can then produce a organic peroxide radicals, RO2, that can then react with a nitrogen monoxide to produce nitrogen dioxide, and these lead to finally the production of ozone. So we have introduced these organic peroxide radicals. Yeah, so, and yeah, so then the fate of RO is different. It can be or oxidized by oxygen, or otherwise it can change its structure, it can be isomerized, it can be thermally decomposed. But one fate is this one that produce again some hydroperoxyl radical that can finally produce some nitrogen dioxide, and so this is a new form to produce ozone. So finally, the net reaction says that the oxidation of these hydrocarbons or volatile organic compounds finally produce two molecules of ozone. And also here there are some hydroxyl radicals that are produced that can accelerate the reaction. So let's now try to focus on how the ozone production depends on the amount of nitrogen oxide. So here we look at concentration of nitrogen oxide that are not so high, and we see that the production of ozone depends linearly on the concentration of nitrogen oxides, while the loss is quite independent on the concentration of nitrogen oxides. And if we now look at hydroxyl radical, they also have their dependence of nitrogen oxide also change. So here we look at the concentration of hydroxyl radical and hydroperoxyl radical, and we see that at lower levels of nitrogen oxide, these two radicals, their concentration is independent on the nitrogen monoxide mixing ratio, while for hydroxyl radical, their concentration increased quite linearly in a moderate, in an environment where we have a moderate concentration of nitrogen monoxide, while for hydroperoxyl radicals, there's still no dependence. And while at large concentration of nitrogen monoxide, what we see is that we have destruction of this hydroxyl radical, these hydrogen oxide radicals. So this will influence as well all the, for example, the production of ozone that we have seen before. We have seen that ozone is produced when carbon monoxide and methane are oxidized by hydroxyl radicals. Here we are seeing that if I imagine a mass of air that is characterized by a large concentration of nitrogen monoxide, we don't have a large concentration of these hydrogen oxide radicals. Okay, and this, for example, has been measured when you have wildfire, when scientists have been able, to do some measurement close to the place where the fire started through some aircraft campaign. Well, they measure really this kind of very low concentration of ozone, because as well you have a low concentration of these hydrogen oxide radicals. So actually this is also observed in cities where you can have a large concentration of nitrogen oxide and you'd have a few concentration of the hydrogen oxide. And so what could be a conclusion is that the production of ozone is complicated, because as well it depends on the amount of nitrogen oxide that is in the system, and we actually can distinguish two regimes. One is called the Nox limited regime, where the production of ozone depends linearly with the concentration of nitrogen monoxide, and the other is the Nox saturated or VOC limited regime, where the production of ozone instead depends linearly on the amount of these hydrocarbons or volatile organic compounds, and is inversely proportional to the abundance of the nitrogen dioxide. Here the scheme tries to summarize all the reactions that include nitrogen oxide, volatile organic compounds, and hydrogen oxide radicals. So we start with ozone that can then, through photodissociation, produce hydroxyl radical. This hydroxyl radical can then oxidize the volatile organic compounds to produce some organic peroxyl radicals that can then react with nitrogen monoxide to produce one molecule of ozone, and then this produce also this RO compound that can then react with oxygen to produce some hydroperoxyl radical that through self-reaction can produce this hydrogen peroxide, or otherwise if you react with nitrogen monoxide, then it can finally produce some nitrogen dioxide and produce one other molecule of ozone, and produce as well some hydroxyl radicals that can then, another sink of all this process is the reaction between nitrogen dioxide and hydroxyl radical to produce nitric acid. So this is a way to kind of summarize all the reactions that we have seen, in particular related to the ground surface ozone. So when you have presence of nitrogen oxide and volatile organic compounds, plus the production of hydroxyl radicals. So probably this graphic is the best way to remember this non-linearity of the system related to the ground surface ozone. So here we have on the y-axis the hydrocarbon emissions, so the volatile organic emissions, on the x-axis the Nox emission, and the solid line represent levels of ozone, and the bold line separate this Nox limited regime from the Nox saturated regime. And what do you observe here? For example, let's think about the Nox saturated regime. What do you see here compared to this region? Imagine that you are moving one member and you are keeping the other fixed. So for example, in the Nox limited regime, if I'm changing my Nox emission, I'm changing my ozone production, right? Because I'm moving towards some isolines that have a larger concentration of ozone. Do you agree? If I'm like, I can, here it's difficult, but if I fix my hydrocarbon emissions, the only way I can change my ozone production is by changing my nitrogen oxide emission. Okay, so here I can assume that here the production of ozone is what we saw before. In the Nox limited regime, the production of ozone depends linearly only on the amount of nitrogen oxide. Okay. Then here in the Nox saturated regime, it's much more complex, because if I fix my Nox emission and I'm increasing the emission of volatile organic compounds, I'm increasing my ozone production. While if I fix my volatile organic compound emission and I'm, for example, if I'm reducing Nox emission, I'm actually going towards some higher levels of ozone. If you fix the amount of hydrocarbon emission that you are reducing the Nox emission, you are increasing the production of ozone, while if you are moving towards higher emission of nitrogen oxide, you are moving towards lower levels of ozone. And due to this, he has been very complicated and is still very complicated for decision makers to deal with problems related to air quality pollution, to ozone pollution. For example, at the beginning, what was thought? It was thought that we were more in the Nox saturated regime. So what has been done, for example, over the US, they try to constrain Nox emission, not so much, but a little bit, because this was during the 70s, and more people were buying a car, so the Nox emission were increasing because of more people using the car. So they try to constrain strongly the emission of anthropogenic volatile organic compounds, and partly to limit the emission of nitrogen oxides. However, they didn't get such a big reduction in the ozone pollution, and this because partly part of the chemistry was not well understood, but also because here we have seen before that the anthropogenic source of volatile organic compounds is small compared to the biogenic source. So one error at that time was they tried to only act on the anthropogenic emission of the volatile organic compounds, and they didn't constrain so much the nitrogen oxide sources. And as well, that experiment led to realize that we are most of the time in a Nox limited regime. So we are most of the time in this kind of situation, because we have quite large, but then it depends on where you are, but for example, in the Mediterranean area or in the US, we have a large amount of hydrocarbon emission from plants, so we can be here. And so the change in Nox emission could really could really change the ozone pollution. Yeah, and so here was just to mention what I said before, that in the 70s, and then really after, we thought that we didn't think about this large production of isoprene or biogenic volatile organic compounds that was much more important than the anthropogenic volatile organic emissions. And so this really brings you from a NOx saturated to a NOx limited regime, and so it limited the outcome of some air quality actions. However, even if we are in a NOx limited regime, still the production of ozone is very nonlinear. And we can see this here referring to one other definition is the ozone production efficiency. That is the ratio between the production of ozone divided by the loss of nitrogen oxide. And staying in with some hypotheses to be in the simplest case, we ended up with the ozone production efficiency that depends linearly on the amount of these volatile organic compounds, RH, and is inversely proportional to the nitrogen dioxide mixing ratio. And what has been the difficulty in all this system is that there's a strong nonlinearity, because what we observe is that if we increase if we increase traffic urban, so if we increase the emission of nitrogen oxide, we are actually reducing the ozone production efficiency. But still we will have some other problems, because nitrogen oxide is also toxic for humans. So instead, if we try to decrease NOx emission, we have to, for example, with model, it has been measured that if we cut by half NOx emission, we can just reduce ozone by 50%. And this because we also have the action of these volatile organic compounds and some other reactions. So this is just to introducing the ozone production efficiency is really to highlight the fact that the chemistry of ozone is strongly nonlinear. So taking a decision to control air quality is really challenging, because you have to really take into account what is the background of your environment, if you have natural emission as well. And as well, you have to take into account the ozone chemistry. Also because, as we mentioned, so we can have this, due just to the ozone chemistry, we can arrive to this, how to say, like a crazy thing that if we increase our NOx emission, then we are reducing the ozone production. But we can't go towards this solution, because NOx are dangerous just in itself for lungs, the respiratory system, etc. However, this explains as well why, for example, the ozone production is the highest in remote regions, because you have low concentration of nitrogen oxide, because you have less sources of nitrogen oxide, and so you have a large production of ozone. And to complicate even more the study of ozone, you have also to take into account all the meteorology that is involved in the troposphere and in at the ground. Today it was probably many things, but I really want you to try to remember some main things, like why the stratospheric and the tropospheric chemistry are different. Remember, for example, that the family that we met yesterday, the hydrogen oxide family, the nitrogen oxide family, in the stratosphere they play the role in the catalytic loss cycles, so they actually consume ozone, while here in the troposphere we saw that they are involved in the production of ozone. And then What else? Yeah, then as well, remember in general that hydroxyl radical, why it is important in the atmosphere, because it consumes some pollutant as carbon monoxide and methane, and this oxidation also produces some tropospheric ozone, and the tropospheric ozone maintains the amount of hydroxyl radicals. So think in an equilibrium system, everything works fine. It's just that now we are, as we mentioned before, we are kind of unbalancing the system by putting more and more carbon monoxide and methane in the box. And then we introduce we moved to the ground surface ozone, and there we introduced these volatile organic compounds that play a much more important role than carbon monoxide and methane, because they have a reaction, they have a lifetime shorter than carbon monoxide and methane. And try to remember about the fact that the ozone chemistry is not just a linear system, it's very highly nonlinear, and remember these two regimes in which you can end it up, in which situation you are. Okay. So do you have questions? Maybe I stop here.